Second round, still 12. Chandler, over to you.
So we ended off on talking about, I'll actually go back to the slide where I was discussing the setting that we're in, just to maybe catch anybody who missed like the first bit up to date. So we're talking about experimental design for causal structure learning. We're starting off by talking about non-adaptive settings, where we pick all of the interventions that we're going to do at a single point in time. We're talking about, previously we talked about bounded size interventions. So interventions where we only have a single intervention target. Now we're going to talk about interventions of unbounded size. So this is where the intervention can have multiple targets. It can, potentially either do a do intervention on multiple variables all at once, or it can change the mechanisms of a bunch of variables all at once. So you can think about something like in the genomics example, knocking out 2 genes instead of just knocking out 1 gene in the system that you're taking data from. We're in a setting where we have no observational data going in. So it's kind of the worst case. We have to deal with any possible graph. Whereas in the setting with observational data going in, we could be dealing with any graph just in a certain Markov equivalence class. And finally, we're going to be still in this setting where we're trying to fully identify the graph at the minimum cost. So the question was, taking all those things into account, how many interventions are sufficient and in the worst case necessary for finding any graph G star on some number of nodes P. And the answer to this question was that we get this floor of log base 2 of P plus an extra intervention. We walked through the proof of this being sufficient. Now we'll go through the proof of this also being necessary in the worst case. And this is going to be like an induction style argument. So we'll assume that the result holds for all numbers less than what we're trying to prove it for. And you can do the base cases for 2, 3, and 4 pretty easily by hand to get you started. So if you do, say for instance, 2 nodes, what is this bound in that case? So the claim is that in the worst case, we need 2 interventions of unbounded size. So we basically have to convince ourselves that we wouldn't be able to identify this in only a single intervention. And this goes back to the argument from earlier and kind of the mistake that I had on the single node intervention case where we have to quantify for P greater than 3. Because if we only intervene on a single node, and we say do a do intervention, so we're setting this node to a specific value, then we won't be able to tell between the case where these 2 variables are independent and the case where these 2 variables are dependent in the observational setting, but we've removed that dependence because of our intervention. Is that clear why this holds when P equals 2? And then we would get, it would still be 2 interventions for 3 nodes and 3 interventions then for 4 nodes. So I won't walk through those, but that will get us started. And then we do an induction argument where now we have P nodes and we say, okay, our first intervention, well, these are unbounded, so it can be on any number of nodes, K in the graph. And what's kind of the worst case that we can imagine? So we pick these K nodes without knowing anything about the graph. And then the nodes that we don't intervene on, if these are all upstream of the nodes that we do intervene on, we don't get any information about them. Furthermore, other than that they're upstream, but we don't get information between these nodes. And then in the worst case, this could be a complete graph over those nodes. And then when we were talking about the kind of adjacency and orientation tests, we mentioned that if we do an intervention that includes two variables, we get no information about them. So if I do an intervention that includes both of these variables, then I can't conclude whether or not there's an edge between them or whether there's, or the direction. So I mean, I don't even know if there's an edge. So of course I can't determine a direction. So in general, I basically have just, in the worst case, partition my graph into a complete graph over the p minus k nodes and a complete graph over the k nodes. And then now, that's less than p, both of those are less than p. So by our induction hypothesis, one of those remaining graphs, so one of them has to be of size p/2 or larger, just because I can at best split it in half. So one of those graphs will require, that should be floor here. I think both of those should be floor. And then because of this division by 2, I guess basically log base 2 of p minus 1, and then I add the 1 back. So that's how many interventions are required to do the remaining part, plus the one intervention that I already used. So that's what's giving me satisfying the induction hypothesis at greater values. Cool. So now we're going to start moving on to, from here on out, we'll be in settings with observational data. Any questions before I move to that about these settings without observational data?
Actually, sorry, it's going forward. So
yeah.
With observational data, I asked earlier, sorry, your essential graph, that's what you call it, right?
Yeah.
And then what I was going to ask here is, in the case of an enormous gene network,
yeah,
there might not be, say there's no observation at all on a subset of this, these 20,000 genes.
Yeah.
What then? Like, can you just put it in undirected edge just in case, or
yeah, so this is essentially, the question was in something like a gene regulatory network where, so like in human cells, we have about 20,000 genes. What if not all those genes get measured? So this goes back to kind of the problem of latent confounding, because you've marginalized out some of the variables in the distribution that you're looking at. So that's going to be kind of this causally insufficient setting that I won't touch until kind of the very end.
The previous setting, are you gonna talk at some point, maybe when you have like a noise or finite samples, you want to minimize those subject to some probability?
Yeah. So I'll discuss some works in like the very end, but everything's right now going to be in this noiseless setting. Awesome. So I'll move on. So now you can see the only thing that changed from the previous setting that we're in is that now we're going to assume that we have observational data. And this is going to require some new terminology to get up to speed on kind of what the algorithm that I'm going to introduce actually does. And I'm going to give kind of the punchline first and then kind of explain the terms. But there's this nice characterization of the interventional essential graphs as satisfying these two properties. One is that it's a chain graph. We'll unpack what that means. And then, so chain graph has chain components, and we're going to say each of those is chordal. And then another useful result kind of in this field is that within each of these chain components, the orientations are of different edges are kind of logically independent of each other. If you orient something in one of the chain components, you can't conclude anything about orientations in a different chain component. Right, so first, and I haven't been saying with all these references, like I'm trying to put as many of the references down here, especially for things that I'm not proving. Right, so A chain graph is essentially a generalization of a directed acyclic graph that's going to have both directed and undirected edges. So this is a different form of mixed graph than we saw in the workshop on causal structure learning, causal discovery, where we were considering bidirected edges. We had two edge types of directed and bidirected. Here, just like we are talking about with essential graphs, it's directed and undirected. So that generally in this talk is going to be what I mean by a mixed graph, is directed and undirected. And we're going to extend the notion of a cycle from a completely directed graph, so a DAG, into a, or just a directed graph into these mixed graphs. So we're going to call a sequence of edges a partially directed cycle. If basically it looks like it could be a cycle with undirected edges, but since we have directed edges, two things have to happen. One is that there's at least one directed edge in this thing, and also all the directed edges are kind of in the same direction. So if I start going this way, it's not like I have a directed edge that way. That would not be a partially directed cycle. If I have another directed edge, it has to be in the same way. Right. So those are the two conditions, and I'm just being lazy and saying that, like, we'll call v minus 1 this vn, so that we can make sure that it's a cycle. And similar to our definition of a DAG as a directed graph with no directed cycles, a chain graph is going to be a mixed graph with no partially directed cycles. And for instance, this guy up here is going to be a chain graph. Yes, if we tried to look for any partially directed cycle in here, we couldn't. There's not. Maybe there are equivalent characterizations where this is a little easier to see. But the main point here is that I wanted to give you the definition of chain components as well. So if we kind of remove all of the directed edges from this mixed graph, and then we just take the connected components of the kind of remaining only undirected graph. So kind of transitivity under the relation of being connected by undirected edges. These will give us the chain components. So we see this one of 4 nodes up here, this single node chain component, and this 2 node chain component. So that was kind of the first definition that's involved in that result. The second definition is what it's a chordal graph. So the claim is that each of those chain components in this interventional essential graph is also chordal. And to define this, we need to say what a chord is, which if we take a cycle of length greater than 4, this is just going to be an edge that connects two things in the cycle that are where the edge itself is not in the cycle, right? So basically something that cuts through and makes this no longer necessarily like a cycle of length 4. I guess it's still a cycle of length 4, but there's kind of this shortcut through it. And a chordal graph is going to just be an undirected graph where every cycle of length greater than 4 has a chord. And these have really nice kind of graph theoretic computational properties that get used a lot kind of in this field of experimental design. One of the properties that it has is that it's easy to find the largest clique in this graph. So a clique is a set of nodes which are all adjacent. So if we just look at the induced subgraph, it's a complete graph. And the clique number of some undirected graph is the size of the largest clique. And I'll be using this throughout this omega G. Yep.
If you take a cycle, you get 2 smaller cycles with those ones, so it be cut by chords. So basically,
Yeah, so you basically cut it down to length 3 cycles.
Okay.
And then, like, yeah, for anybody who's worried about, oh, are we going to be using the clique number like computationally in any way? Are we going to be trying to find like the largest cliques and stuff? That's usually an NP-hard problem. In the case of chordal graphs, this can be computed efficiently, I think, in linear time. Another thing that can be computed efficiently that we'll be using for chordal graphs is this idea of a coloring, which is just an assignment of colors to the graph, such that two adjacent nodes are not the same color. So for instance, this is a coloring of the graph on the right with 4 colors. And similar to the quantity that we had for the size of the largest clique, we can ask for the size of the smallest coloring. And that's going to be called the chromatic number of the graph. I don't really use that term. It is very convenient for chordal graphs that the chromatic number is actually equal to the clique number. So the clique kind of tells you how many colors you have to use, and then you can be clever and reuse those colors that you used on the largest clique kind of throughout the graph. And again, this will actually be used computationally. And this next algorithm is being able to find an optimal coloring of a graph, so coloring of the smallest number of colors. And that can also be done efficiently for chordal graphs. Okay, so now we get back to our question that motivated all of this kind of technical material, which is how many unrestricted sized interventions are going to be sufficient and in the worst case necessary for determining some the true graph out of some Markov equivalence class. And the answer now, instead of depending on the number of nodes, is going to depend on the clique number of the essential graph. And here I'm being a little sloppy with notation. So typically we use the clique number to, it's a function of undirected graphs. The essential graph can be a mixed graph. But because we have these chordal chain components, what we can do is just look at each one of those individually and take this clique number to be the size of the largest clique in any of those. So that's just a note on kind of my sloppy notation here. And I also don't know if I kind of harped on the notation that I'm using for the essential graph. So previously I was saying with the subscript of the interventions, that's the I essential graph. Similarly to the Markov equivalence class, I'll just remove the subscript when I'm talking about the observational setting. So this is just your plain old kind of essential graph, no interventions involved in its definition. And luckily the strategy looks a lot like the strategy that we just saw. So instead of assigning each vertex a distinct number, we're going to first find an optimal coloring and then assign the colors a number. And then we're going to use kind of the same construction for the intervention set. So the example will be probably more clear than the text. So that was the graph that we had earlier. That's an optimal coloring of the graph. We can just think of these colors as corresponding to numbers, and I'm writing out their binary representations here. So I have 4 colors, so now I should be able to do it in 2 interventions. And the way that I do that, so I look at what my definition is. The first intervention has to have the targets be everything whose color has a 1 in the right-hand position. So that's the purple and the blue. And then the second one is going to be the orange and the blue. And by the fact that this is a coloring, this is going to guarantee that any 2 adjacent nodes will have at least 1 intervention that targets one, but not the other. Yep.
Yeah, so these results are for the first case. And I was wondering if there is some literature that connects graphical features into number of interventions that we're expected to perform.
Yeah. So the question was, all these results are in the worst case, or they're basically results that kind of more graph specific that use the graphical features to tell you about how many interventions you might need to perform. So the answer is yes. Some of that's going to be in the end of the talk. I think that's kind of more preliminary, so it's not super well developed. But there are some kind of graph-specific bounds that you can get on the number of interventions that are necessary, even kind of Markov equivalence class specific bounds for that as well.
And one more question. I know you said that we are going to look at the case where causal sufficiency doesn't hold.
Yeah.
Later section.
Yeah.
Just quickly comment. When we have causal insufficient settings, why we cannot use these bounds as well?
Yeah.
Because the way I feel about it, even if there is an like unobserved confounders, if we're intervening, then I feel like it shouldn't be that much of a problem. But yes.
There are ways to do it with interventions that are unbounded in size, but there's some counter examples to when you only have single node interventions, you can't even hope to actually pinpoint the graph.
Yes.
So it depends a little bit more on what the kind of experimental limitations that you're dealing with are. And I think that's also, I mean, there's like the two results of unbounded and like single node, but then there's probably open questions on what comes in between those. Awesome. Okay. So I just wanted to pull out a few papers that I'm not going to be going over here, but just kind of links to these results if people are interested. So when I was talking about the bounded case, I was really just focusing on bounded by one. I wasn't giving general results for when the size of the interventions are bounded by some other number. So say maybe in genomics experiments, you're doing knockouts and, oh, actually I can do 2 or 3 at a time. And I want to see, you know, how much better can I do if I'm allowed to do that instead of just one thing knocked out per intervention. So that case is covered in this paper, and I had an interesting question during the break. It was basically, you know, like we have this kind of logarithmic dependence on the number of the clique size in this case, or like in the case with no observational data, the number of nodes. We had this logarithmic dependence when it was unbounded, and we had this linear dependence when it was bounded, like to kind of smoothly interpolate between that. And this is essentially going to provide like a positive answer to that. Not at risk of, you know, confusing people and speaking out of stuff I don't know too much about. This uses this construction of separating systems on graphs. People know what those are. And it kind of uses results from kind of classical graph theory literature to prove stuff about this kind of interpolating case. And you will see like the linear term, as you add more interventions, kind of gets divided by the number of interventions, and then the log term kind of starts creeping in. So it does kind of interpolate between these. And then I've also, as I mentioned, maybe at the beginning of the first section, focused on really minimizing the number of interventions that are done, and kind of assuming all interventions cost me an equal amount to do. So you can imagine this is not always going to be the case. Maybe some things are harder to intervene on. Maybe I can't even intervene on some things. There's kind of an infinite cost where I can't include that in my identification strategy. And there's a paper that essentially extends this one, but allows for costs on the nodes as well. Yeah, so these are interesting things to check out if you're into that sort of stuff. And now I'm going to move on from this kind of minimal cost identification setting to a setting where you have a fixed budget, and show you some of the things that can be proved about that setting.
Just as an idea, I'm wondering, is there in the literature anyone that has tried to explore something like, I don't know if can be even modeled in the causality, strategic observation, that we cannot observe everything, but we have to incentivize the people in order to give us the observation and how that interferes with the causality. I'm trying to merge the two workshops.
Yeah. There's something that does, in some active sense, pick the interventions, or sorry, the variables you're going to be observing. But I'm not sure how related it is to this literature. So I would look up like picking observed variables or active learning of like observations or like something like that in the causality literature. But that's the only thing I know of. Also, yeah, obviously the room is full of experts on this stuff. So if anybody wants to chime in with other stuff that they know about, feel free to do that. Okay, so now I'm going to be, I guess, moving to the setting with a fixed budget. So now instead of saying these kind of questions of like, oh, how many things are sufficient and in the worst case necessary, I'll say just given a certain amount of interventions, how much can I learn? And my task is going to be to maximize, in this case, so it's going to be the first place where we're using expectations instead of kind of this worst case analysis. And just for simplicity, and this is actually, I think, what's done in the paper, we're going to be using a uniform distribution over the Markov equivalence class. So you can think of this as if my level of identifiability only gives me the Markov equivalence class, there kind of should be no difference between two things in the equivalence class. Otherwise, somehow my prior or whatever I'm using to get this different distribution over the Markov equivalence class is baking in that some graphs are preferred over others, which may or may not be your setting, but if you're kind of focused purely on what you can identify from data and no additional assumptions, the uniform prior is natural. And then this isn't like kind of real notation, but this is just going to be counting the number of directed edges in this I-essential graph. So I'm trying to maximize the number of directed edges. I'll kind of go through in the adaptive part how there's other choices that you might be interested in about how much information that you have, but we'll see that this one suits itself to kind of combinatorial optimization techniques pretty well. And as I said, we're going to be doing single node interventions, and we're going to be choosing K of N. So the point about it actually being good for combinatorial optimization is that this function we're going to end up trying is submodular. So to review what submodularity is, this is a property of set functions. So functions that take in sets, we'll assume that we have this like total set or like universe omega, and we can take in any subset and return a number. It's submodular if you have this kind of diminishing returns property. So if I have a set A that's contained in a set B, then adding the element B to A increases the value of the function more than if I added the value B to the larger set. This shows up in a bunch of settings, and it's kind of like a general way that like you can think of many information theoretic quantities working. If I have a certain amount of information A that's less than the amount of information I have B, like whatever function I'm using to measure how much information are in these sets, adding to the smaller set is going to kind of end up giving me more information than adding to the bigger set. And we'll see how this comes about with these directed edges. And then a second definition that we need for these types of functions is that the set function or submodular function is going to be monotonically increasing, just if having more things in the set gives me a bigger value. And there's kind of a natural way you might think of optimizing this greedily. So if I'm trying to find the set of size k that gives me the best value of this function f, instead of enumerating over all subsets of size k, what I can do is just pick one element at a time. So I start from the empty set, and then I see what element I can add that most increases my function, given kind of the current set I have, and then I add that into my set. So at each time, I'm just evaluating however many different things are in the set, and then adding it in. So this is a much quicker thing than kind of this enumeration of all subsets. And kind of classical result, combinatorial optimization, is that if my set function is both submodular and monotonically increasing, then this greedy optimization strategy will give me an approximation guarantee. So the thing that I'll get is within this factor of the actual maximum.
So now your items are the possible interventions.
Yes,
Isn't there exponentially many of them because because
single node
size,
interventions.
but if it's unbounded size, then you can have exponential.
Yeah. So I don't think the proof here is going to extend to unbounded size interventions. And the theorem is essentially that if I fix a graph and I take in this intervention set, then if I let the function just measure how many directed edges I have, then this function is monotonically increasing in submodular. But this does rely on this being the set of single node interventions.
So
one comment to add that is also interesting is actually it's not even monotonic anymore if you intervene on multiple nodes. So that makes it really difficult. But you actually have you can prove non-monotonic submodularity and then proofs based on that.
So one of the things here, I think, is that your objective, so the average of monotone modular functions is monotone and submodular.
Yep.
I think that you can't evaluate your objective well.
Great.
Or at least you have to sample. You're not going to know it exactly, right?
Right. Yeah. So the point is the objective I'm trying to optimize is this expected value over graphs in the Markov equivalence class. Now we haven't discussed too much yet about the size of the Markov equivalence class, but if you imagine like a Markov equivalence class of a complete graph, I can choose any permutation of those vertices. So I have p factorial. So generally these can be very large. And one of the reasons I picked this to talk about is there's actually nice, pretty recent sampling algorithms for picking uniformly at random from a Markov equivalence class in polynomial time. And that's like within the last 2
Is
years.
that like they can do it exact
Uniform sample.
Oh,
Yeah.
wow.
Yep.
So if you use this approach, you're kind of already hoping only for approximation guarantee. Is it known that it is hard to get exact?
I mean, I think with maximizing submodular functions in general, it's known that it can be NP hard to get the exact maximal. With this one, I'm not sure if there's any other structural properties that would lead to it being easy to get exactly. So I don't think there's a proof of like a NP hardness reduction or something there. Good one. But nobody's proved that it's easy. So that's why we're doing submodular optimism. All right, so this proof relies on this interesting fact that to me was at first counterintuitive, that if we have two sets of nodes or two sets of edges that we get from separate single node interventions, so we have this E of I1 and E of I2, then if we take the so this, right, like this could be I1 is a set of single node interventions. So we could have one intervention on, like, say, node 1, one intervention on node 3. So this isn't, just a single intervention. The elements are each singleton sets. Then if we take the union of the edges that we get from both of these, so basically you think of, I start with a bunch of edges that I learned from one intervention, and a bunch of edges I learned from another intervention. Now I mix those together, and I ask if I can orient any more edges. The answer is no. So their union is actually complete under the orientation rules that I think were discussed on Wednesday. They're kind of boring, so I didn't include the orientation rules again. We'll talk about kind of an example of how this plays out for a specific one, but it's a kind of tedious proof. So I just want to give you the flavor of it. But why would this imply submodularity? They have kind of the same feeling, and then kind of just walking through the proof. The number of edges that are oriented if I add I. So because of this, the only edges that are additionally going to get oriented if I add a single node intervention I to this existing set of interventions are exactly the things that are oriented by I if I hadn't already done those other interventions first. And then I'm subtracting out the things that were already oriented. So I also have to do the set difference there. So the kind of submodularity condition reduces to this just checking that these two set differences satisfy this inequality, and that's like a trivial inequality.
Is this here many proofs saying that EI1 union EI2 is equal to E the union?
It's the same. Yeah. Yeah. So the point is that I could have equivalently said, and I think this is actually the way that it's written in the paper, that I1 union I2 equals.
Can I interpret this theorem as another proof for why P minus 1 interventions is enough?
I had not thought about that, but I think you probably can. So the question was whether you can derive essentially from this theorem the proof that you need P minus 1 interventions.
Not need, but it is.
But is sufficient.
Because you just take union, right?
Yes. So it's P minus 1 single node interventions. We get from each of those interventions all of the adjacencies to that edge, and then we just union over all of those adjacencies. So yeah, this is a good point of sufficiency. Okay, so the kind of sketch of how this proof works is the first thing that we think about doing is we check the preconditions for invoking any of the meek rules that involve more than 2 edges. Because how would we get more edges from meek rules than we had in one of these original sets? So if it only involves one orientation, then whichever set that orientation was in is kind of sufficient to invoke that meek rule. So it has to be that we have one of the edges that's invoked in this that kind of activates this meek rule coming from the one set and the other edge coming from the different set. But you can, the kind of proof technique is to show like whenever this happens, the existence of one of the edges in the first set would imply the other edge is actually, so this should be I1 is also in the first set. So actually it would turn out that we didn't need the second set at all. To kind of demonstrate more specifically, say that we were to invoke this meek rule that tells us to avoid cycles. So we have x1 to x2 and then x2 to x3. we can't make a cycle here, so we would be invoking it and direct x1 to x3. So we check, all right, so maybe this edge is from the first set of edges that we learned, and this edge is from the second set. Okay, so let's say it's just this edge that's in this first set. Well, we know this edge can't have been directly from an intervention, because if we got it from intervening on x1, then we would have also gotten this edge. And if we were to get it from intervening on x2, we'd have also gotten this edge. So that's ruled out. And now we have to check if it's from any of the other meek rules. So there's kind of 2 layers of meek rules that we have to check here, which is why this gets pretty tedious. But for example, one of the meek rules is we can't create a new V structure. So perhaps we say, perhaps I got this edge because actually there's this other variable A that points into x1, but does not connect to x2. And that's going to give me, and if I already had this edge from A to x1, then by the fact that I don't yet have the edge x2 to x1, I have to orient it this way. Okay, so maybe this A is out there and it's pointing to x1. Now the claim is that, okay, there's 2 circumstances. So I said A is not connected to x2, but I never said if it's connected to x3 or not. It could be either. So if it's not adjacent to x3, then I would get this orientation the same way. So also by invoking this kind of not creating any new V structures rule. But if it was actually adjacent to x3, then there's another meek rule that gets invoked. So you can essentially see if I had this edge and it invoked that this goes this way, and that these 2 are adjacent, then I can't orient x2 to x3. So I'll do this on the board. Okay, so I'm saying that I have this edge, that gives me this edge, and then I'm asking, can I orient the edge x2 to x3? Well, if I did that, I would form this, I can't orient this way, or else I'd form a cycle. So I know that that's oriented this way. And then because of this, I also get that way. But now I've created a new V structure between A, x3, and x2. So yeah, you get this very case-based analysis that shows you this interesting fact that just combining the sets of edges that you get is going to give you, no new meek rules being invoked and giving you extra edges. And that is enough to show the submodularity of this function. As Chris pointed out, a positive linear combination of submodular functions is still going to be submodular. So that's what I have here in monotonic. And then the question is, how do we efficiently approximate this expected value? As kind of suggested, we're not going to actually enumerate everything and then average it all up. We can do this kind of by a Monte Carlo averaging technique where we just sample a bunch of things and average them until we get within some comfortable epsilon. And the way to do that is in this recent paper that shows you how to sample from the Markov equivalence class with this setup time that's bounded by essentially the square of the number of maximal cliques, which is also, you can see in Chordal graphs that this is going to be bounded by the number of nodes. So this is essentially kind of at the worst case, some kind of low polynomial in the number of nodes. And then that's the setup. And then we just sample from it pretty fast. It's kind of linear time and the number of nodes and edges. So that's all for the setup on kind of passive experimental design, non-adaptive experimental design strategies. I think it's easier to just go into the adaptive ones after lunch. So if anybody has any questions, I could take those now.
It seems like if we are doing interventions, single not one at a time,
Yeah.
we'll also be doing, like in addition to identifying, we can also be doing estimation.
Yeah, so the question was, can we do estimation? I'm assuming you mean of kind of the, if say we're in a linear setting, estimation of like the linear regression coefficients or something. And yeah, so generally interventional data will help us estimate everything that's not involved in kind of the thing that we're actually intervening on. So if I had this graph like x1 to x2 to x3, and I intervene on x3, the data that I get on x1 and x2 from that intervention is still perfectly good for kind of estimating this linear regression coefficient, or more generally, the distribution here.
If you're into the central variable, yeah, identifying an edge of
Yeah,
this
estimation.
on like the path to its chunk.
So are you asking about something besides estimating, kind of like given a graph, what the parameters are of the graph?
So suppose your ultimate goal is not just identification, some, some form of regression or selection.
Yeah.
Could you also do that iteratively because you're doing investigation? Is that you're doing integration?
Yes. There's kind of two separate things that we could imagine using experimental design for, like picking our interventions kind of to maximize. One is the information that we obtain about the graph, kind of help us identify what the graph is. The other one is specifically to learning kind of parameters of the graph so that we can make predictions with it in the future. So I'm not too aware of work which explores simultaneously wanting to do both of those. There is work that I'll mention in the last section on given a known graph, how do I pick interventions that kind of maximize my ability to infer my parameters. And that's a little different than kind of the classical experimental design setting, at least as far as I understand, where you, and by classical, I mean like not for causal structural models, but for, kind of, how do I pick inputs that allow me to learn, say like a linear regression well or something, because of the relationships between the variables. So yes, picking say a value for x1 that you kind of want to use to maximize your ability to like recover this conditional distribution doesn't just maximize your ability to recover that one, it also can help you recover this distribution. So that paper kind of goes through some of the details of how you kind of combine all of the information that you might be getting and like pick interventions that are kind of optimal for that rather than just doing it separately.
I'm not sure if this is a good question to ask, but what you just showed us was that if you place additional assumptions like chordality or submodularity, obviously very nice things happen.
Yeah.
But in a real world scenario, like are these fair assumptions to make?
Yeah. So the question is like submodularity, chordality, are these fair assumptions to make in the real world? I think not. I see this as a starting point, and kind of maybe analyzing deviations from that. So how far off of chordality, how far off of submodularity of this function would, how will that impact? Like what can I kind of tolerate?
maybe I'm mistaken, but it didn't seem like submodularity was an assumption that you made. It was
Yeah.
something that actually
Yeah,
happened. Given
no, so right, so neither of these are assumptions that we make. Chordality is also derived from the kind of details of what interventions allow us to learn in the graph, but I guess both of those are kind of predicated on assumptions kind of further back in the stack, and especially with estimation error and stuff. We saw, for example, with the causal structure discovery lecture that the kind of conditional independences, there might actually be kind of conflicts in those, and you have to have ways of resolving those conflicts. So assumptions that are made in kind of the population setting don't always necessarily translate to things in the statistical setting. Like you might not be confident enough to direct one of your edges in your intervention, but you might be confident enough to direct some of the other ones. And that would break, say, like the chordality property. And I could also see something like that breaking submodularity.
Yeah. Well, for what it's worth, just putting it out there has been a lot of work in the submodular optimization, community where, this 1 - 1 over E result was if you could access your function exactly.
Yeah.
Here, your function is an expectation.
Yeah.
Which I could sample from that
Yeah.
distribution.
Yeah.
But I probably can't,
Yeah.
exactly estimate the expectation.
Yeah.
But there is work in the submodular world, like, okay, my submodular function is the average of many of them. I can perhaps sample.
Okay.
This leads to some I can't estimate my oracle. I don't have an oracle for the function exact. So there is work in that. I don't know to the extent to which it's been plugged in here.
Yeah.
But that does.
Not that I know of, but it shouldn't.
So it has, so Andreas Krause is one of the submodularity. So the plugging in of, for example, using like non-monotonically increasing submodularity for these problems.
But not even non-monotonic. I guess I'm referring to like.
But the same for the expectation was also introduced
Okay.
by him. But yeah, I think there's a lot to be done there. I think, just one person is not enough to get the whole community and it would be fun,
Because was saying Andreas Krause has done some work on this and has looked at some of the experimental design for causal structure learning problems, just plugged in some of the results, but there could be more.
I just want to understand, in typical gene knockout experiments, are those interventions more like do interventions or more like soft interventions?
My understanding is that it's more like soft interventions. So you'll downregulate. I guess in a true gene knockout, you would completely actually remove it from the cell, but there's different technologies. So I think it varies by the technology.
So does that mean it's actually better than the worst case of that they proved in those theory?
Yeah, so is it better than the worst case? I think that you might need a few additional assumptions on the kind of way it changes the distribution. So it kind of like, this faithfulness thing or something, like technically within the class of soft interventions are do interventions. But if you assume specifically that you rule those out, you rule out perfect interventions, then you at least retain this dependence information between interventions, which is kind of, one of the problems that we have. So I think you would be able to do better if you analyze specific cases. About that. Awesome.
Okay. I also don't see any more questions. So we'll take a break till 2 o'clock as always for lunch. Thank you very much, Chandler, for the first.